All right, this is AP Calculus, Unit 4-2, Lesson 4-2. So today we're talking about tangent line approximations. So, opening up, we have approximating with a tangent, our example problem. So, 18 inches of snow fell on the first day of a terrible snowstorm in my hometown of Colfax, California. And at the end of the first day, the snow continued to fall at a rate of 12 inches per one day. So, we're going to use the equation of the line tangent to approximate the snow at time 1.2 days. So,
is it a real story?
No. Colfax never got this much snow. I probably should have just used Mammoth.
I was going to say, Colfax near like Sacramento.
It is. Colfax is about 25-ish minutes north of Sacramento on the 80.
Oh, whoa, that's really close.
So, we're going to go ahead and say that snow, we're going to say we have a function s of t. So, a function depending on t. That means we're going to plug in a time value and we're going to get out a snow value. Snow in inches per day. Or in inches, sorry. So s will approximate the number of inches. So if s of t is my function for height of the snow, what is s of 1?
12.
12, yeah. Well, be careful here because I'm going to say 1.
Give me time.
That's okay. It's not quite right because s of 1 is the height of the snow. So I'm going to tell you some more information. Well, we have the more information right here. So 18 inches on the first day. So be careful here. It's not 12.
That's 18?
It's 18 because 18 is the height after the first day.
But I had the right idea.
You did. So what is s prime of 1?
0.
Here. I shouldn't have told you.
S prime of, well, what is a way to translate this into English? S prime of 1.
So maybe it's 30.
No, s prime of 1. Not s of 1, but s prime of 1. The derivative.
0.
0.
So you're saying there's no more snow being added?
Oh.
12.
This is 12.
1.2. Oh, that's what I meant to say.
12. This is saying that the rate, s prime is the rate at time equals 1. So at exactly 1 day, the rate is 12 inches per 1 day, or 12.
Okay.
Okay, so we're going to use this information that we've analyzed from our problem in order to find the line tangent. So this is just like homework from yesterday now. We have this information. What is our line tangent?
So we
So we need to
have...
solve for.
We have it. So like... Right? Because 1 would be...
Oh yeah.
Would be y
So we
minus
just plug
1.
in.
Sorry, y minus 18
Y minus 18.
is equal to...
12. X parentheses
Parentheses.
X
Minus 1.
minus 1.
Minus 1, yeah. And just in case we forgot the equation of the line tangent, I can write that over here. That's y minus
Blank equals blank.
the y coordinate. Yep. That's good, Isabel. Yeah, you got to memorize.
Blank minus blank.
Yeah, so before I move too much further, what is 1.2? Obviously, we can plug that in and then we'd find the answer, but let's think about it in the context of the question. 1.2 days, what time am I really asking for? When do I wake up? Oh, it's 1.2 days right now. What time did I just wake up at?
I feel like that's something you would say. This is what I said. That's something you would do.
So what is it? What did I just say in a normal language?
It's like a certain amount of hours.
Morning. Yeah, a certain number of hours. It's getting closer, getting warmer. But it's an exact time. And what is the exact time?
26.
Yeah, so we can think of that as 20, is it 8 or 26?
26. Because 0.2 is 2 hours. And then it goes from 24. Yeah, that makes sense.
0.2 is 2 hours.
0.2 is
So that means at 1.9, that's 9 hours.
1.2 is like an hour. Wait, no, it's not. 2 hours. No.
So 1 day is 24 hours.
More
0.2 days is
Isn't it like 30 minutes? I don't know.
like either. I
Wait,
don't know.
what?
How do you solve that? Do you do 24 divided by 0.2?
Okay, so on the
A half,
23.
or it would be.
Wait, why did I say 23?
so let's say we have 0.2 days, and how many hours are there in a day?
24.
Okay, what is this equal to? 4.8.
Oh.
Me too.
4.8. So it's roughly, and then what's 0.8? 0.8 hours is how many minutes roughly?
That's like a lot.
0.8 hours is how many minutes roughly? And then we'll stop there at minutes. We could go to seconds and milliseconds and everything after that. 0.8 hours. Well, let's do 0.8 times 60. 0.8 times 60. 48. Yep.
Nice, Joy.
So this means I am at 4:48 a.m. in the morning.
How do you figure that out? Oh.
Assuming that this t equals 1 is at 24 hours. I think that's a valid assumption to make. Okay, so moving on. That was kind of trivial, but let's actually do our math now. So I don't actually know what the function looks like. The function, don't write this down, the function could look like this, and then just happen to be at this point, the slope was 12. We're going to approximate, I'm going to guess that another 4 hours is within that interval that I'm allowed to approximate. So how do I approximate the time at 4:48 a.m. using our linear function? What do we do?
Well, we plug in 1.2.
We're going to plug in 1.2, exactly. And I'm going to do that on the right-hand side. Give yourself room on the left-hand side to make a graph. So plugging in, we have y minus 18 is equal to 12 times 1.2 minus 1. I'm going to add the 18 to the other side as I simplify. Y is equal to 12 times what?
0.2
0.2. Keep going for me.
plus 18.
18. And simplify this all into one number.
Psych.
Okay, maybe I should back up and show my work. Let's do
No,
2 times
you're
12.
right, I did
That's
something wrong.
48. Move the decimal. I did something wrong, I
Wait,
think.
what? No. It's 22.
It's 24. I did it right.
No, it's 2.4. Yeah, it's 2.4.
Yeah, I did the math right at the very end, but I just made a mistake right there for some reason. Plus
18,
18,
which is 20.4.
20.4. All right. So our answer in the context of the problem, what does this mean?
So at 4:48 a.m.
Yep, at 4:48 a.m., what do we,
there were 20.4 inches.
exactly 20.4?
Yes, approximately.
Approximately, yeah, that's the key word there. So let's go ahead and make a graph of what is happening here. Because we always need to be thinking in context of what the function actually looks like. And I guess it would be better to make the graph because we're only in the first quadrant, so maybe make the graph more like this.
Oh, sugar nuts.
So we knew, and we can graph some points here, we knew that from our blue data that we had at time, this is going to be my time axis, this is going to be my height of the snow. we knew at time equals 1, we'll say 1 is right about there. Oh, that's not time equals 1. We'll say, sorry, that's not right. Time is down here. We'll say at time equals 1, we got up to 18 feet. So we'll say that's 10 feet. We'll say this is 20 feet. So roughly, we'll make this a skinny little dashed line. Roughly at 18, coming out here, and 1, this point is where we were. We knew that that was on our graph because I knew I had 18 inches and I knew that was at time 1, at the end of the first day. And then from there, we knew that we were making our tangent line with a slope of 12. So a tangent line with a slope of 12. So slope of 12 is pretty steep. It goes up. It's probably even steeper than that.
Wait,
but
what if we don't get it exact?
it's fine. This is just an illustration.
Wait, we should be drawing this too, right?
Yes, keep drawing everything that's here. And we wanted it to approximate over here at 1.2.
So do we usually use the approximations when it's like something really close to like another number? Like
That's the only time, in fact, yeah.
But, okay.
If it's really far away out here at 3, it's probably not going to work. It might have stopped snowing on the 3rd day. I think we can assume that if it was snowing at 12 inches per one day at the time, at the end of the first day, it's probably going to still be snowing a few more hours in the distance in the future.
We should have to have calculated snow melt, like the sun.
Our equation, if we actually had that in there, more variables, we could have gotten a more exact date,
But we don't.
more exact height. We approximated, we said, well, it looks like this is where it's heading. Using our function, we were able to approximate that, hey, at here, 1.2, we got, and then maybe I can make my lines fancy just like I did before. So at 1.2, it looked like I was getting a height, if I drew it straight, a height of 20.4, which, again, the graph doesn't do it justice because it's not scaled correctly. But it looks like over here, we're at 20.4.
Oh god, I got near 30 for me.
20.4.
Yeah, mine is not.
The main thing to understand here, maybe I should have put days. The main thing to understand here is that we had this value, we knew what it was, and we knew what the slope was. We were able to approximate on this line what our value for our height of the snow was. So I guess what I should have been writing here this entire time, instead of saying equals, we should have been doing approximately. So I think just for the last one, I'm only going to erase one, not all of them. On this one, I should have been writing this is approximately equal to, because it is an approximation. It's probably not the same slope for this entire time. And I have one line that I can write here on this slide, so I'm going to write this. So I'm going to make this assumption. For my t, I'm going to make this a little bit to the right. For t, it's going to be between these values. I'm going to tell you that these are the number of days that I know how much it snows. Between 12 days and that first day. Between the first and 12th day, I knew this. S double prime of t is greater than 0.
It's 12, not 1.2.
Nope, not. Well, I guess that would make more sense, right? 1.2. I knew that the s double prime of t was greater than 0. So I need to be able to draw a conclusion from this. Therefore, or this implies, our approximation was, and then the question is, was it an underestimate or an overestimate?
It was over.
Okay, so this is where we probably want to refer to our notes from 4-1.
Oh shoot.
Was this an over approximation or an under approximation?
Over.
No, under.
Because we know that S double prime was greater than 0, so it's going to be an over. 'Cause
That's-
that means it's concave up.
It's concave up. I agree with your analysis so far, and therefore
Oh, so that means down. That means under approximation.
under approximation. So I hear Joy and Kaylin saying under approximation.
Wait.
Yeah, it's under.
Sophia
Okay.
also jumps on the bandwagon, says under. I need to hear from Carly and Isabel. Under as well?
Under.
Under as well, yeah. Therefore, our approximation was an under approximation. And we'll fit this in here. Under. And that's because it was concave up. And maybe you want to label this. This meant concave up. All right. So, main thing to take away here that concavity does matter. Concavity matters. Sometimes I'll give you concavity in terms of S double prime. Sometimes I'll just give you a graph. But you do need to find concavity. All right. Here's the last question that I'll ask, and we can write this down if you want. The last question is, what if concavity was equal to 0?
Then our approximation was perfect.
Exactly, yeah. If concavity was 0, then that is a linear function. And therefore, since we already have a linear function to approximate what's going on, we have an exact solution.
So it's a continuous slope.
Yeah, exactly. The slope doesn't change, it's continuous. All right, so that's all I have for us today for our notes.
That's it?
That's it. All right. Do you guys want to say hello or goodbye to Rosalie?
Bye, Rosalie. Feel better. I don't know where you are.
Bye.
Yep, bye Rosalie, we miss you.